Unit 1, Introduction to Engineering, Part 2 of 3. What is the engineering design process? What methodical processes do engineers use to solve problems? The engineering design process is similar to the scientific method. Most engineers have their own twist for how the process works. The process generally starts with a problem and ends with a solution, but the middle steps can vary. The design process is a three-step loop. First, we're going to ideate. Second, we're going to implement, and third, we're going to test, and then we'll go back to ideate again. Step 1, ideate, an idea is generated. Step 2, implement, the idea is put into practice. In Step 3, test, the idea is tested and the result is evaluated. During Step 3, additional ideas are generated and the process starts over again. This cycle and repetition is why it can be said that design is an iterative process. Iteration is the act of repeating something over and over again in order to improve the process and eventually achieve the desired goal. Using the engineering design process. We will use an 11-step design process to conceptualize, design, and create a robot. Engineering design process steps. 1. Understand. Define the problem. Step 2. Explore. Do background research. Number 3. Define. Determine solution specifications. Number 4, ideate, generate concept solutions. Number 5, prototype, learn how your concepts work. Number 6, choose, determine a final concept. Number 7, refine, do detailed design. Number 8, present, get feedback and approval. Number 9, implement, implement the detailed solution. Number 10, test, does the solution work? And number 11, iterate. Step 1, understand. In this step, engineers will define the problem they are trying to solve. This is the single most important step in the design process. In robotics, there are typically numerous problems that need to be solved by the design team. Some sample problems a designer may encounter that need to be solved and questions that need answered are: how fast does the robot need to move? How can the robot pick up an object? How can a robot pick it up quickly? Step 2, explore. In this step, engineers will do background research on their problem solving. They will investigate the ways others have tackled similar problems. Engineers will also gather details on the environment they're dealing with, the situations will be used in, and the ways it will be used. Step 3, define. Engineers will specify what the solution will accomplish without describing how it will do it, usually through the use of specifications. What are specifications? A specification is defined as an explicit set of requirements to be satisfied by a material, product, or service. Specifications typically come from two places. 1. Design constraints, and 2. Functional requirements. A constraint can be defined as a condition that a solution to a problem must satisfy. Functional requirements describe how well the finished solution must perform. Specifications outline what the solution will do and how well it will do it, but not how it will do it. Thinking too much about how at this stage in the process can be counterproductive and may stifle creativity. At the same time, designers need to keep the how in the back of their minds, because they need to have a basic understanding of what is possible. Define specifications ranking. All specifications are not created equal. Some are more important to the design team than others. Specifications are often ranked in some way to denote their importance. One scale is W for wish, it's not important but it would be nice if possible. P, preferred, it's important, but the project won't fail without it. And D, demand, critical to the project and it must be included. Designers must make decisions about what is most important when they apply these rankings. Ranking the specifications in this way will also make it clearer in the designer's mind what to focus on. The constraints required by the design challenge itself are ranked as demand. Example: robot can hold 5 balls, that's the demand. Robot can hold 10 balls, that's preferred. Or robot can hold 15 balls, the wish. Through the use of good specifications and ranking it, it's possible to outline exactly what requirements the design team should follow and what goals the design team should strive for. Step 4, ideate. Ideate means to formulate, imagine, or conceive of an idea. Napkin sketches refers to the habit of jotting down ideas whenever and wherever they occur, even if you have to jot them down on a napkin. Formally documenting sketches may help when solving complex engineering problems. The designer needs to brainstorm multiple ideas to fulfill the specifications. Good designers will look in the world around them and try to find solutions to adapt to their problem and build off of. Innovation is also important early in the design process. Don't wait to innovate, always put innovation first. Engineers should record all ideas in their engineering notebook. Brainstorming. Some important rules for brainstorming. Number 1. When brainstorming, teams focus on the quantity of ideas generated, not the quality. The premise is that from lots of ideas will come a few great ones. Reserve judgment. There are no bad ideas during the brainstorming session, because even the most outlandish concept could inspire someone else to come up with something great. Crazy ideas may also be improved and developed during the collaborative process and become feasible ideas. And number 3, record everything. Student designers should document all the ideas generated during brainstorming in their engineering notebooks. Step 5, prototype. The goal of this stage is to learn how each concept solution will function in real life and how it interacts with its environment. The key word here is learn. Designers don't need to prototype everything, just the things they want to work. Step 6, choose. This step is where the designers will use the lessons learned from their prototyping to determine which concept is best and go forward with it. Teams can compare how each concept fulfills the specifications from step 3 in the process and see if one is significantly better than the others. When choosing concepts as a design group, it is tempting to rely on a vote. However, a vote is nothing but an unjustified opinion, and an unjustified opinion isn't worth much in engineering discussion. As an example, one shouldn't say something is better. They should say it's 14.8% lighter. Decision-making tool weighted objective tables. One tool used to help during the concept selection stage of the design process is the weighted objectives table, sometimes referred to as a decision matrix. Here's some examples here. Step 7, refine. This is the stage of the decision process where engineers take their chosen concept and make it into something more real. This stage is all about details. These designs will start off very basic and evolve as more details are added. Stage 8, present. The detailed design must often go through some sort of design review or approval process before it can be implemented. Many reviews involve presenting the detailed design to a customer, manager, or some other decision maker for final approval. Stage 8, present. Common questions from a design reviewer. Why was it done this way? Did you think of doing it a different way? Why did you rule out other alternatives? Does it fulfill our requirements and specifications? How can we make it function better? How can we make it weigh less? How can we make it faster? How can we make it more robust? How can we make it smaller? How can we make it simpler? How can we make it more efficient? How can we make it cheaper? How can we make this easier to construct? What other functionality would be easy to add? Cost-benefit analysis. When performing this kind of analysis, a designer will look at an aspect of the design to see two things. 1, what it costs, and 2, how much benefit it provides. Cost does not always refer to money. A feature's cost refers to the resources that must be diverted to it. These could be time, personnel, money, space on the robot, weight, and more. It could also refer to items that must be sacrificed in order to implement the feature being analyzed. For example, if we build a two-jointed arm, we won't have room for a ball intake on the robot. Features that provide a big benefit at a small cost are the kind that should be added to the design. High-cost items should only be implemented if they provide a big benefit. Stage 9, implementation. Depending on the nature of the problem being solved, the solutions to the problem could vary widely. The implementation could consist of using a new process that was designed, or it consists of following a manufacturing plan and producing some physical object. If an engineer is trying to solve how to tie shoes faster, they are designing a process for tying shoes. Their implementation would be to tell people about their new shoe tying procedure. If an engineer is trying to design a better shoe, their implementation would be to manufacture and sell the shoes. Implementation can take many forms. Stage 10, test. In this stage, engineers will test their implemented solution to see how well it works. The implementation must be reviewed to see what worked, what didn't, and what could be improved. The main thing that should be determined during this stage in the process is whether or not the final implementation performs as expected and fulfills the specifications. What happens if the design is not found to be acceptable? The design group must find a way to make it acceptable. The design group needs to come up with a plan of improvement to get the solution up to snuff. Step 11, iterate. The act of repetition is known as iteration. This iteration results in a better end result and is one of the most important parts of a design. One important thing designers should note is that iteration does not just take place at the end of the process. It will happen during every stage of the process. The design process is not a linear thing. It is common to jump from step to step. Design teams should not be afraid of going backward in the process, repeating parts of the processes to improve the final result. The greater the number of iterations a design goes through, the better the final result will be. So why would a designer stop iterating? The law of diminishing returns. Improvements to the design will get smaller with each successive improvement. Eventually, the designer may decide that the next improvement is too small to be worth the effort, and the design is good enough. Some designers take longer to call a design finished than others because they strive for perfection. Unfortunately, in the real world, it is not always possible to achieve perfection. In the real world, if an engineering contractor misses a deadline, they may not get another chance, and they may have trouble finding other contracting jobs. Subsystem design. There are often smaller design processes within the main design process. This ends section 2.